Hello everyone, Namaste, good morning, good afternoon and good evening to all of you participating from the different corners of the globe. Well, it's late afternoon here in Nepal, that is 5:45 local time. I am Sudip Phuyal, electrical engineer and automation professional, and I am currently working as technical expert in the research project entitled Microgrid Management and Control Systems to provide efficient energy solutions to the mountainous region of Nepal, funded by Ministry of Foreign Affairs, Norway, at Department of Electrical and Electronics Engineering, Pokhara University, Nepal. Also, I am the co-lead for the project RoboVan, the COVID-19 dead body handling robot, funded by Nepal Academy of Science and Technology. Moreover, I am the co-founder of Robotics Academy of Nepal and also the co-founder of Institute of Himalayan Risk Reduction, Kathmandu, Nepal. As an alumnus of Pokhara University, I am currently contributing here as an advisor of Robotics Club, Pokhara University, and will be moderating this webinar entitled Importance of Distributed Generation and Microgrids for Rural Electrification, organized by Robotics Club, Pokhara University. Firstly, I would like to welcome you all in this webinar, and this is the continuation of our webinar series, which we have been conducting to continue the learning process even in this COVID-19 pandemic. We have already organized various trainings and webinars for the undergraduate as well as graduate students during this lockdown period by virtual method. We are excited to see the huge number of registrations from different 23 countries, and altogether we have more than 150 registrations. To address such a huge request, we are recording this session, and also we will later upload our video in our YouTube channels, and we will send the links to all the registrants who have missed this session due to some technical issues or something or their personal some problems. And now we are focused to deliver the webinars as Robotics Club Pokhara University is focused to deliver the webinars by the experts in various fields, which enhances the understanding of the topic in depth, supports the students and researchers in the particular subject area, helps professionals and early career scientists to broaden their knowledge with the insights and healthy experience sharing by the experts in the same field. And our webinar series will include different research areas of electrical and electronics engineering and will be organized in a monthly basis. On behalf of the organizing team, we are really grateful to our distinguished guest speaker, Dr. Sudip Phuyal, who is the professor and William investigator at Department of Energy Technology, Aalborg University, Denmark, where he is the founder and director of Center for Research on Microgrids. Before entering into the main session, I would like to welcome Engineer Bhutiraj Joshi, who is the former dean and also former acting vice chancellor of Pokhara University, and also would like to welcome Associate Professor Lalit Vikram Rana, who is the coordinator of MSc in Electrical Power Systems Engineering program and also the senior faculty member of Electrical and Electronics Engineering Department at School of Engineering, Pokhara University. Mr. Rana is also former dean of Faculty of Engineering, Midwestern University, Surkhet.
Yes, thank you. Thank you very much for your kind introduction, Sudip, and for the invitation to this seminar. I hope that this will be the first step towards the collaboration between Denmark and Nepal in terms of microgrids. So that's why we wanted to call this the importance of distributed generation and microgrids for rural electrification. Yeah, so first of all, before starting my presentation, I want to tell you, please don't believe a word what I'm going to explain here. Yeah, everything can have a lot of mistakes and errors, so please verify it. Verify everything, not only checking, but also trying yourself. I think it's very important to do. I want to also dedicate this presentation to Ziva Rostami for the work we have been done in collaboration and also for the past birthday. So happy birthday. And I hope that our collaboration can continue from here. Some words about our situation right now. We have, according to the United Nations, still 2.7 billion people without access to the electricity. And we know this, that a lot of fancy things are coming, let's say with a lot of technology, but still we have this problem. And I think that we have to look on the context. Yeah. Something about me. Well, this is a little bit what I have been studying, but of course I have been studying many other things, so nothing else. Regarding what we call the sustainable for development goals that has been defined by United Nations, I think it's very important that in the past United Nations, they had goals to help, let's say, some parts of the world to increase the sustainability. But right now these goals are global. So let's say that there is no a single country, not a single region that escaped from one of these goals. So that's why it's kind of becoming very important right now. And I would like for you to take the chance to read each of these words and think what is the meaning for you for each of these goals, how we can really achieve those goals, and what you can do for contribute on that. This is the situation right now in Nepal. We have around 11% of the Nepali rural population, which is about 23 million people with access to electricity. And one of the problems is that it's too expensive to put power lines, or let's say distribution or transmission lines across a country which have so many mountains, and the geography doesn't help so much. So many people who live in those remote villages, still they use kerosene and maybe batteries. So that's really a problem, especially looking at this kerosene. So one of the possibilities is to use, of course, microgrids. Yeah, and we are not going to define here microgrids, but we know that here our goal is to include, let's say, renewable energies close to the consumption points. And I will say that from the perspective of the Nepali, let's say, situation, it's perfect to think on this way. Yeah. And we know that there's many definitions about microgrids, nanogrids, picogrids, but for me, most important is the philosophy that is behind that, right? So it's something that we cannot even define in terms of levels of powers, because it depends a lot on the application. Well, something about our university. Our university, we have here, one of the departments is the Department of Energy Technology, which we belong to, and we focus on different, let's say, kind of energies. I will say all of them renewables. And inside the department, we have our center, the Center for Research on Microgrids, looking on different aspects. Yeah. You can see here the different frameworks we tackled, from interconnection of different microgrids to maritime microgrids, till more fancy microgrids with IoT and digitalization, and microgrids also in space. Yeah. This is also a picture from our members. So thanks for our members also to assist to this talk, and also for the work and help every day. Yeah. This is some of the pictures of our laboratories. Just for the people who don't know that, each of these table, it's connected to a setup which emulate a microgrid, let's say in the order of 10 kilowatt each one. And we make also experiments interconnecting a number of microgrids between them. The good thing here is that we use just MATLAB Simulink, which maybe a lot of engineers are using, to compile the code and to just test our ideas over power electronics converters. As you can see here, we use a number of converters. In that case, we use 4. And then thanks to this digital signal processor, we just convert these MATLAB Simulink files. We test it in real time with the, let's say, real equipment. And we have here also some smart metering equipment. So this way we are able to emulate different things like having solar panels, batteries, and loads without having to connect real systems like batteries or photovoltaic systems, because we can emulate them from what we call hardware in the loop system. Yeah. And the next step, which is also very nice, is to use a multiple of these microgrid systems to be interconnected together in a distribution network. So I believe that this also could be of the interest in Nepal. Some pictures from our labs here also. We have also a living lab with a real wind turbine and some photovoltaic systems. And inside we have also a home, let's say, with many fancy things. Let's say that is kind of a smart home. We have many appliances that we can control. And we control also all these devices through smart metering. And also some other, this is also another smart meter, but faster than, let's say, the commercial ones. And this is how it looks like our demonstration house. So we have on one side, we can test algorithms very, very fast. On the other hand, we have a demonstration house in which we can maybe make more real tests. Also, one day, very tired of just trying things in the laboratory, I try to do also this myself in my house. So I decide to install solar panels and to use an electric vehicle. I encourage all of you, all the one that can do that, of course, if it's in your possibilities, to try to go as much as possible in these directions, because you can have effects like doctors taking your own pills. Everyone knows that my favorite doctor is Dr. House, the one who inspired me. And for me, most important is, okay, you can try to find many excuses in your life, but if you want to do something, you will really find a way. And this is very important. I will say that at the same time that for Dr. House, major part of times the illness was lupus. When I look at controllers, for instance, for microgrids, normally with PI controllers, it was more than enough. So it's something that I try to abandon and try to think on different aspects. I'm going to show you some examples, try to face more reality and escape from, let's say, fake research. Yeah. Another important thing for me, and I think that many people know that, it's how neuroscience it's affecting us. And when you think about neuroscience, of course, you think that our brain is made on a number of neurons interconnected with synapses, and all this is electric. So we have to think that what we have is an electric system. And what is more important here is that when you have thoughts, these thoughts generate reality, and these thoughts also are able to change matter. And you say, how it's possible the thoughts can change matter? You have to think that every time you have thoughts, you are wiring networks between neurons and neurons, and this is energy converting to matter. And this is something I would say amazing. Yeah. And the other thing that also amazed me is the amount of neurons that you can find in different parts of the body, and how this is also linked with some of the traditions like the chakras, and how also the different waveforms that we have are corresponding to these chakras. Some people say that we just use 5 or 10% of our brains. This is basically not true. We use 100% of our brains. So be happy to have this brain fully working. But however, we only can use simultaneously 2% of that brain. So that means that you activate different parts of this brain, but only 2% it's connected because of these limitations of glucose and oxygen. What happens is that normally we use similar neural network paths. And one good thing is to try to use different paths, right? To avoid these constant, let's say, thoughts that are coming every day and we cannot read off. Yeah. Another interesting thing is to see how our brain itself also have like three layers. Let's say that one is the reptilian brain, which is basically 500 million years old. So basically reactions, action reaction. Then we have the limbic brain, which belongs to the mammals. And this is more where we have the feelings, also where we have different parts of memory also embedded. And finally, we have the neocortex, which is the more rational part. And it's the more, let's say, new. So now we can understand also why our decisions are more based on emotions. You can imagine 200 million years. It's kind of a difference comparing of only 100,000 years. And then it comes the neocortex saying, okay, I'm going to give a justification for my decision. Yeah. Another interesting thing is also how also stress can be good. We have been seeing that we have listened a lot of times that stress is not good. And I will say that it's good if it's in some level. Once you pass to some level, you can start to have exhausting, fatigue, and finally burnout. So it's very good, let's say, to have a certain level of stress to go to an optimum activity. And I think that that's also very a nice thing. And this is thanks that positive stress generates dopamine and noradrenaline, which allow us to have more let's say, excitation for learning, having more motivation, and to be more alert. Another very interesting thing is about how our brain feels trust or fear. It has been a research study that demonstrate, very, very recent, that demonstrate that trust and fear, it's originated at the same places of the brain. Are basically three parts of the brain. And that means that you cannot basically have trust and fear at the same time. Yeah. And this is, I think that's very interesting. And also we can see that we have two empathy systems. One is the logic empathy, which we use more the tempo-parietal junction. And the other is the emotional empathy. So this is thanks to the mirror neuron system. Yeah, you know that we have all this neural network that is mirroring. So we have this empathy when someone, for instance, is suffering, or for instance, when someone is happy. So that's, I will say that this is very important. And the other important thing is how our brain also communicates with the 40,000 neurons that we have in the heart. Yeah, so this communication basically comes from the heart to the brain, and there's not so much communication from the brain to the heart. So now we can understand that when we have some feelings like love, gratefulness, and even hate, this is basically activating those networks and giving some information up. So one of the more exciting research that has been done also is regarding the heart rhythm patterns. So it's not good to have, let's say, a heart rhythm which is basically stable. It's good to have it changeable, and then it is changing according to how is your breathing. Yeah, I'm not going to go in details with that. If you have interest, we can go and discuss. But some experiments has been done also. We know that the heart have a electromagnetic field and can be measured in 2 or 3 meters. And this magnetic field also affect other hearts. We have seen how two people going together and maybe having feelings of love each other, without touching each other, their hearts can be synchronized. And in many other cases, also this has been researched, also with animals and so on. That's why also it's so important, for instance, once for people that are alone, they could have, for instance, some especially a mammal next to this person. Yeah. So after looking at this, which is very interesting, let's go inside the microgrid field. So let's see the microgrid configurations. Basically, when we have a microgrid that can be connected or disconnected from the main grid, we need a connection interface. And then we need a number of power electronics converters to interface all those components. Not always we have power electronics to interface, but some of them may have. And that's very interesting because you could also connect different microgrid systems in the level of, for instance, 400 volts, low voltage, and put it up to the level of medium voltage. So this way you could have a very rational viewpoint of how to build an electric system. You start building microgrids here and there, and then you interconnect them with the distribution system in the level or in the medium voltage level. And then we will see maybe you can connect also to the high voltage and go to what we call the main grid. But what is the main grid? Something that we build from inside out if we take the microgrid philosophy. Another important thing, many people look at generation, and I will say that loads are very important. And it's very important to see when we can disconnect some loads, which kind of loads are shiftable. For instance, when we think about a freezer, we can just shift this load and use as a thermal storage. Yeah, we saw these examples in some installations, which is kind of very exciting research, I will say. The other question is, should we work more on AC or should we work more on DC? And I will say, I will not care a lot about this. The most important is to find, when you have to build your microgrid, is to find the appropriate product or equipment to use that. And then you can see, and it has been demonstrated that the efficiency is not so different. It was maybe very different in the times of Nikola Tesla and Edison, because at that time you could not raise the voltage. It was not any kind of DC transformer, but nowadays I will say that is comparable, let's say. So it's becoming kind of equal. And if you ask me my opinion, if I have to choose a transformer or a power electronics converters, for terms of reliability, I will always choose a nice transformer. Yeah, especially if it's for a real application. In case of DC, of course, we can see some products available. For instance, Schneider Electric has been put for India some example of products to have 230 volt on DC to transmit around 1 to 2 kilometers. So that's also a possibility, right? And if we go to AC microgrids, you can see here some examples. I will say that this is very interesting because that's in Jeju Island. And this island is disconnected from the grid in Korea. So they have their own grid. And they are combining wind power with wind turbines and solar PV together with small hydropower. So I will say that this is also very interesting as a case in which also you could think how from the Nepali geography, we could integrate hydropower and microgrids. Some other examples, I always like to put this example from Japan because they really combine, let's say, CHP system, so combined heat and power plants together with renewables. And that's also something very nice because also you can kind of increase the efficiency by taking the thermal losses from your engines and put it back to these digestion chambers that will produce gas. The other example, and I will say that this became a paradigmatic example of the microgrids, it was the Sentai project in Japan, which is 1 megawatt microgrid system supporting hospitals and telecom centers. And it has been also very famous because during the disaster in Fukushima, they survived to this disaster and they support for 3 whole days the hospital and the communication systems. So it was a very good example to show how microgrid technologies and renewable energies can survive even disasters sometimes produced by other kinds of energy. I'm going to give you here one example of collaboration. And this collaboration has been done with Tsinghua University and the company Shanghai Solar. And here we have been developed a microgrid system in several steps, let's say. And all of these steps, we have been following the IEC codes. So we have IEC standards for power quality. Then we have also IEC standards related to SCADA systems and communications, and IEC standards also for EMS systems. Yeah. Finally, this is another IEC standard for smart metering. So I think it was very interesting to see how we could install this in a building. And the building was with solar photovoltaics integrated PVs and some inverters developed by Huawei. And then we also erected a couple of wind turbines. And then those wind turbines also we connected to a couple of back-to-back converters. And finally, we developed also together with Tsinghua University a bidirectional inverter with a battery system. And also we have been test islanded conditions. Yeah. So also that's very nice because here you have also the website and also some reference. These some pictures. We are talking really about around 130 kilowatt solar PV. So you can see here also the Chinese authorities with us checking the installation. This was at the end of the project. And then here are the two wind turbines erected and the connection to the building. Yeah. Then here we have the lead acid battery system. And it was, all this was in the basement of the building, and then a couple of wind turbine converters. And here it was the main switch for make the test of islanding operation. And all these cables are cables that are coming from the roof, which are these solar inverters. We develop also the energy management system for them. And right now it's working and in operation for a long time. Another important thing that I would like to say is that when you try to build photovoltaic systems, you have some inverters which are more designed for grid connected operation, and some others that are more designed for islanded, right? So in the past, we just had to use one of these possible, let's say, systems. Right now, there are more and more, let's say, equipment in the market. So I will say that is a very good moment for microgrid deployment. Yeah. It was some time, let's say, for make a lot of research and things like that. But I will say that, and that right now we passed the moment of having pilots. And I will say that this moment is for large-scale deployment. And I will say that this is really exciting. You can see some products in the market, like if we take, for instance, SMA, with this, for instance, the Sunny Boy, it's just a bidirectional inverter connecting battery systems, and then many others that you could also integrate on the DC side, on blue. And then in the red side, you have the AC part. Then those Sunny Boy, you can see that also they have frequency response. So that's very nice, not only when you are connecting to the main grid, because in the main grid also, if the frequency is too big, means that I have to reduce the power. And this is a way that I can move out from the maximum power point. And they come also with, at that time, it was a patent called self-sync, in which they integrate basically frequency and voltage groups. Yeah. What they introduced, let's say, as a different is, it was a term to change directly the frequency in order to improve, let's say, the transient response. So we have like a frequency group, which is frequency versus power group, and then they introduced this. Another important thing is that those two filters add additional inertia In that case, it was something that you could assimilate with a synchronous generator, like adding the mechanic torque and also the electric excitation. So I will say that was very nice the way that they present, and I will say that this almost becomes a standard. Of course, they were not the first to develop Druck controllers, but they put in very nice products. Many other companies, for instance, Fronius, they not only integrate, let's say, solar photovoltaics, but also converters to connect to battery systems and probably diesel generators. And you can see here that we have a very similar curve. So once we surpass this threshold, in that case was 51 Hertz, then the MPPT curve goes out. And this basically, you can regulate this curve according to how much is your grid code. So your grid codes will tell you how to do it, or maybe your microgrid, if it's a microgrid system, then you have to adapt these frequency ranges. One of the research that we have been done is by using those kind of equipment. So you can just take bidirectional converters with batteries and solar PV systems. You can see here that the battery converter is just taking the state of charge with a very easy estimator, let's say. And then with this, we change the frequency. If we are, let's say, outside the ranges, I will explain this now. So that's, all these things are very classical. Let's say we have a voltage loop and a current loop, and then we just change the frequency according to how much is this state of charge. At the same time, this is the inverter control. And then the inverter control is doing the opposite. It's trying to inject as much current as possible, going to an MPPT algorithm. But then if the frequency go out of ranges, it starts to affect the algorithm and to decrease the power. Yeah, so I will say that this is kind of the representation when you are inside the state of charge reasonable. And when I say reasonable, it depends on the technology. So you have to see what kind of battery you have there. And maybe if it's fine to work between 40% and 80%, let's say, then you will fix these two state of charge limits. If the state of charge is higher, then automatically the frequency will increase. So we'll follow, let's say, the rules of the power systems. Too much generation, frequency starts to raise. And of course, if our state of charge is too low, then our frequency will go down. Automatically, you can see here what happened. If the frequency go down, our PV panels decrease the power, and they find finally a common operation point. So that's very nice because we are kind of, I will not say that is exactly adding inertia to the system, but it's kind of making the system dependent on the state of charge of your batteries. Yeah. And then if you look here, if the state of charge is too low, you will start disconnecting loads. So that's why I was saying that it's important to look on the two dimensions, generation and also loads. And this way you will automatically regulate the power. This is not rocket science, right? So I will say that controlling a microgrid is very easy. We don't need very fancy things. Yeah, that's why we are able to do that. And then you can see here a little bit more about how is the operation. So this is the PV curve of a solar panel. When we put them down, let's say, it's because automatically we saw that the state of charge maybe went too high. And then you can see here, if it's going too high, the frequency will increase and automatically our power will also decrease. Yeah. So this is basically the mechanism, how it works. I will say that it works very nice, and many companies are also using this principle. Another example of our research was by using hydropower and, let's say, photovoltaic systems and batteries, how we could integrate all of them. And this has been implemented in a project in China, in Tibet. And we did this work with collaboration with the Chinese Academy of Science. And you can see here in one hand, we had the hydropower plant. And I put this example here, because the good resources you have in Nepal about hydropower. So I don't want to here propose very fancy things. I want to really try to, by looking at what are the equipment available right now and making small changes, how we can make something great, which is increase the level of renewables. Yeah. So here you have the model of the hydro plant. This is in the level of 35 kilovolt. It's a medium voltage. And then here there's a transmission line. And then we have the connection to, let's say, our microgrid system. The microgrid system is using the 3 levels of control that we have been developed for many years. So basically trying to add inertia to the battery system, and then trying to adjust frequencies and voltages here, and also to control the power flow from and to the hydro plant, right? So here you can see, well, the system. Here is the model of the system. So this is the hydraulic governor with the frequency droop integrated, let's say. And then this is the solar battery system. Let's call this is like the microgrid. And then here is the hydro turbine generation and excitation system. This is what we have, let's say, and this is how we have to integrate it. So we had to add, of course, part of these high-level controllers, as you can imagine. And then here you have the whole plan. So this is a 2 megawatt peak photovoltaic plus battery system. And then 17 kilometers later, in the medium voltage, we have another connection first with the first hydraulic power plant. And then later on, we have the second one. You can see here the test that we have been done also, making, let's say, changes in power and looking at how frequency and voltage could be stabilized thanks to this system. We have been also developed some lab scales models. So we just downscale all those models to test in our labs. And we just use a couple of inverters to have, let's say, what we call aggregated models. So we took one aggregated model for the hydropower station and the second one for the solar plus PV station. Yeah, and with these two aggregated models, we add in the top of those models the controllers. You can see here we have the excitation system model, and also we have everything related to the hydraulic turbine and the servo motors. And on the other hand, we had those controllers that there are, let's say, in the microgrid system, in the solar plus battery system. Yep. We made some tests. So you can see here with a very simple lab scale cabinet, we just make some tests by using MATLAB Simulink. And then this is real waveforms. You can see here the frequency response of the system and also how the power was changing. So in red, you have the hydropower response, and in green, you have the microgrid response. So I think that this was very nice. And I would say that at the same time, we were able to publish in an IEEE transactions paper. So sometimes I can see a lot of people afraid of using real things to publish. And I will say that this is the best way that we can do research that is useful for also for future generations, right? So that's very important that we start developing those models. And I will say that it's very nice. And of course, if you want to do any kind of collaboration, we are open to also offer our cabinets to test your ideas and also reproduce what happened in other parts. Okay, that's all from my side. And I want to finalize with an important statement from Arnold Schwarzenegger. He said, you have to remember that during his mandate in California, he said, the future is green energy, sustainability, and renewable energy. Thank you very much. That's all from my side.
Thank you, Professor, for your very insightful presentation. Okay, I would like to request the participants if you have any questions, you can unmute yourself and you can ask and you can discuss the issues. I can see Chetan Raj, he's raising hand. Chetan Raj, are you listening to me?
Yes,
Yeah,
sir. Yes, sir.
yeah, you can put your queries here.
Yeah. Yeah. Hi, sir. Yeah, sir. Like whatever you are showing the slides, PI controller or PR control. So whatever you have done analysis, which control is suitable for power converters? Like different case studies you will be doing. So which controller is more suitable to parallel, droop control for parallel converters in microgrid? Thank you, sir.
Yeah, thanks. If you think about droop control is even simpler than a PI controller. It's a P controller. So I will say always the simple, the better. Try to find always the simple solution. Yeah. So of course there are many controllers that maybe work, but it's different when you have to, for instance, design a very simple controller, which what is doing just an automatic control, you know, like following a reference. Sometimes it's relatively easy. I will say that the more difficulty here is to use high-level controllers like energy management systems that maybe in some cases they will need some kind of prediction. But this is all only in some cases. Major part of the cases, if you just want to regulate, let's say a value, I'm talking about, for instance, primaries and secondary controllers. PIs are working very well. And of course, you can convince me that you can add many other things, but let's see the trade-off always. So I'm not saying that PI is the best. I'm just saying that PI is the 90% solution that we can see in the market in many applications. So that's why maybe we have to think about when we try many kind of controllers, at least to first try to use a PI, but the best tune as possible, because some people try to compare with a PI which is not well tuned, right? So I will say that I didn't want to be very critical with the comparison between Lupus and PI, but you can see that there is a lot of these things ongoing now. So yeah, I would say that everything has their own, let's say, focus. If you think about optimization, maybe you need, okay, like managing energy or power, maybe you need very complex things to do. Or sometimes a lookup table is good, right? So I will say the simple, the better. If a PI control works, why we have to invent something that maybe it will be more complicated? We can, of course, compare performances, but performances are good, but don't think that sometimes I can see, for instance, algorithms that achieve THDs of 0.1%. I can tell you in a distribution system, if you reach 5%, it's more than enough. So nobody will pay you for having 1% of THD. Just one example.
Yeah. Thank you, sir. Thank you very much.
Thank you. Thank you, Chetan.
Thank you.
Is there anyone who wants to
Yes,
ask your queries?
I have one question, please. My name is Fernando Antunes. I am from Brazil, from the northeast of Brazil. I have met Professor Guerreiro sometimes. It's
Hi,
very
Fernando.
nice, Professor.
How
are you? To hear you. And
yeah.
I have one question. It's your presentation. This was fantastic, like the other one. I mean, I learned a lot of things, and I think not myself, but people that listen to you. And I want to ask about inertia. Sometimes I'm a little bit, I have a little, let's say, concern about we are putting a lot of microgrids into the power system. Okay, today the level is not that big, but I think in the future, maybe the inertia would be a problem. And I mean, the lack of inertia, I would say. And the presentation that you mentioned now, maybe we have solved the problem with the group control of inverter. What's your opinion about this, please?
Yeah, it's a very good question. You know, it was last year a blackout in UK. One big power plant went down, and automatically, few time after, an offshore wind power plant detects that the frequency went down, and automatically they shut down. So right now we have in question, I'm not talking only about small PV plants that are connected in houses. I'm talking about offshore wind farms that are still working like a current source, just trying to put all the power that they can. And once they see that the frequency is going down, they just disconnect. Right now, there is the discussion of how those offshore wind power plants or even some other renewables can also support frequency and voltage. And I think that there's a lot of discussion about this. And I will say that it's an economic thing. You have to, why the people who's installing offshore wind power plants don't like there to support frequency and voltage, because they will lose power injection, which is money. So right now we have to think how we can incentivize all these guys to say, if you support my frequency and voltage, I will pay you what? Otherwise will be difficult. Or I will have to put more constraints in the grid saying, if you don't accomplish with this, you will not be able to connect here. So right now, some people even are trying to say, okay, maybe I could put part of my plant. For instance, it was a recent study that they look at how many percentage of your wind turbines can operate in grid forming, because of course you don't want all of them working in grid forming. So which is the minimum percentage can be acceptable, and then maybe this can go to the market. So I will say that this is a global thing, no? Because we want to go on renewables, and at the same time we want also stability in the grid. So yeah.
Okay, Professor, thank you for your
answer. Thanks, Fernando.
Okay, thank you. All right.
Thank you.
I stay here.
Yeah, thank you. I hope everything is good in Brazil.
Yes, I think it's good.
Yeah, excellent.
Yeah, trying to survive with that pandemic, yes, but things are going okay. We are going to a low level. Okay, that is not sorry.
Hello.
Yes. Hi, Anand.
Hello, sir. How are you, sir?
How are you?
I'm fine, sir. Sir, just one question. Like whatever frequency curves you have shown, in that large undershoots are there. So what we can infer from that? That's all I just want to know. In frequency curves, whatever frequency curves you have shown in your slides, in that large undershoots are there while settling. So what we can infer from that?
You mean that when we have an overshoot in power, the frequency will go down very fast?
Yes, sir.
Yeah, that's correct. Indeed, this is the effect. You have a large overshoot of power, let's say, and then the frequency will go down very fast. But this is what we try to, if you have a system, let's say faster, you will have a larger overshoot. If you have a system which is slower, so with bigger inertia, this is going to be slower. So in this sense, I would like to maybe distinguish two things. One is the frequency drop, like when the power increases, we have a frequency deviation, and this is static. And the other one is a transient, you know? So it's just going and maybe going back. So I will say that if you want to improve the transient response of this, what some people do is they add a derivative term, or they use, if you think about frequency, they use a PI control. Yeah, we go back to the PI control.
Yes, sir.
Or you act, as I show you, over the phase. So you could act with one loop that changes the frequency, and another loop will change the phase, which is basically the phase will be a change of frequency, but just in the dynamics. With this, you could adjust those overshoots if you have some problem. So you will reduce the overshoot by adjusting with this additional parameter. Basically, all these methods do exactly the same. If you take mathematically, it will be the same. It's the same to take a PI control over the phase, it's the same that taking a PD control over the frequency, or it's exactly the same that is done by SMA with the self-sync operation, which they change frequency and phase with 2 separate loops. Yeah, so that's basically the solution.
So that means it will be better to have slower dynamics or faster dynamics it is required in this case. Just this I'm confused.
That's a very good question. If you have an isolated system, let's say, and dynamics are very fast, why not having the system fast? The problem is when you are connected maybe to another system which have a very slow dynamics, maybe you want to also slow down your dynamics, and then you could adjust the dynamics of your system according to the one who you want to share in parallel. Depend on what do you want to achieve, you know. For instance, sometimes some people come to me and tell me, look, I have a battery system, or I have some super caps, and I would like them to support with peaks of power. So then I will say, okay, it's the other way around. I want this system to be very fast and just actuate with the short periods and very, very fast, let's say. And with this, you know, so you have to accommodate on what you have behind. I cannot give you a general answer because the different devices that we have are not general. It's not the same connecting PV panels than connecting super caps, you know. So you have to decide on, depending on what you have behind.
So, sir, there must that some certain limit should be there for that overshoot. Is there any, or we can adjust accordingly like you have explained?
Yes, what we have is a limit, let's say maximum around 2% of frequency deviation.
Okay.
And we cannot accept changes over more than 1 hertz per second. This is not something that I'm saying. It's normally the regulation in UPS systems. What you have, it's this limit. So I'm talking both in static and dynamic. Statically, let's say 2% of frequency deviation. Dynamically, no more than 1 hertz per second.
Okay. Thank you, sir. Thank you so much.
Yeah, thanks. Okay, thank you, Rafa. I can see that some people is leaving. It was some questions also written. Can we explain here?
Yeah, sure.
Someone said, why, Abderazak, hello. Why communication systems are still not well adopted by industry in power electronic application? Depend on what you mean on communication system. Because if you buy some equipment for your house, you will have a communication system with through internet, and you will be able to follow it. What kind of communication system do you want? So that's my question. So I will say that there are a lot of inverters that accept, for instance, Modbus. And for major part of the applications, it's useful. So I will say that this is changing. And right now we have more communication systems that are able to do this kind of extra, let's say, operations that we want to have. Another person, Nietzsche Shakia. It says, if two AC systems are connected with back-to-back voltage converter, can active and reactive power be exchanged simultaneously? Yes, they can be exchanged simultaneously. And I will say, of course, respecting to the PQ static function that the converter have. Yes, so always respecting this. If you are inside it, it's not exactly a circle, but let's say if you are inside this PQ region, it's perfectly okay. I will say that in some applications you can feel that back-to-back converters are expensive, but there are some experiences like ABB install a back-to-back converter in a microgrid village in Finland. And because the power quality was really very bad, so they finally used the same back-to-back converter that they are using for wind turbines. I think it's an amazing experience to say. If I jump in some question, please forgive me or put it again. There is also Muhammad Bilal say, what is the effect of virtual inertia to change transient response? Okay, I think we answered already these questions. Yeah, I don't know. I think that's all. If I forgot some question, please let me know.
Yeah, also I would like to request everyone to raise your hand if you have questions or you want to ask your questions verbally. Also, you can write your queries in the chat box also. We will wait for a few minutes for the questions and then we will proceed further.
Yeah, also Shethan, you asked about hydropower microgrid and solar battery microgrid shown in the slides. What are the challenges you face in the parallel operation? I will say that the challenges we faced is like you have two systems with very different inertia. So you have very high inertial systems like the hydropower and the other with very slow, very fast dynamics. And with power converters as well, and you had to put all these things in the medium voltage. So yeah, it was a challenge also from the viewpoint of, let's say, technical, and to put all these things together in the level of 10 kilovolt. Yeah.
Okay, I guess
Yes.
we don't have any more queries, or I think okay. Okay, we don't have any more queries here. Thank you, respected Professor Phuyal, for making your marvelous presentation and allocating your valuable time here for this webinar. And also, we are looking forward for a long-term collaboration in near future. And also, would like to thank all the participants. And also, I would like to inform that we will share the links of this recorded webinar very shortly. And okay, would like to see you all in our next series of our webinar also. Thank you everyone for being here. And once again, would like to thank Professor for such a wonderful presentation and also giving your valuable time for us.
Yeah, thank you. Thank you very much. Thank you very much, Sudip, to the organization, and also for all the friends that are always connected here, and also the new ones that are in this talk. So thank you very much. I appreciate it.